In this session, we look at the dynamic response, more specifically the step response curve for first order models. We take the example of this tank system. We saw that the model can be expressed in the form of a linear ODE as we use this level here as HT, this input to be FT, and to express the variable in their deviational form. Also, we took the Laplace transform and found that the Laplace domain, we express the level as this equation. You said that this function that transfers the input variable into output variable is called the transfer function. And you said that for Fs equals some value m over s, we end up getting h prime t to be km 1 minus the negative t over tau. So that was the solution of that particular model equation. Now if we want to look at how does this function look like, okay, so we have this level inlet flow here. We said that it changes in a what is called a step manner. So at time t equals 0, it goes from some value to another value. Now we wanted to figure out how this function would look like if initially the level is at some value. How would that change? Now to look at the shape of this function, let's look at some common functions. Suppose if you plot some common functions, so this is our time. Again, some function, suppose this one is ft equals a constant, suppose a. This one is another function, suppose ft equals bt. Okay. So this function will look like, so it can be something like ft equals a plus bt. So the function that will be interested in this case is something called as exponential function. Suppose an exponential function, with this our value 1, this one will be something like e to the power, say, any constant c t. So this is an exponential function. Now another function, if I take, suppose this is e to the minus q t. Okay, so this is an exponential function. This is an exponentially decaying function. Okay, so in light of this general shape of the functions, how does this look like? Now if we want to plot this, let's express this as two functions. One is km minus km e to the negative t over tau. And let's plot these two parts separately and subtract this one from the other one. So if we try doing that, these are time axis t, and we plot km, it will be simply a constant function Km. And for this part, you see for t equals 0, this part becomes 1. So for t equals 0, this part becomes Km. So the function will start here. And for it's an exponentially decaying function, so we'll have something like this shape. So we subtract this one from this one, we end up getting a function of this form, like this. Now we can see that, okay, many physical process, real chemical process, if we make a change in a step way, meaning if we change, say, input in a step way, the output changes like this. So if we look at now this height, if this is your time 0, corresponding to when you change the inlet flow, from here it should go like this one. Okay. Now what does this shape of this curve say? Now if we look at the first equation we started with, we end up getting something like this. A2 say this is your f minus whatever our value was for f naught. So if these are f naught, this was this. Now what happens that if f is, if you change f, that remains constant, and with the change in f, the level start going up here. And we know that this f naught equals some function of this level here. So if f naught h goes up, f naught goes up. So what you're seeing here, if f remains constant, with the increase of h, the f naught goes up, meaning that as we are subtracting f naught from f, dh over dt will go down. Simply meaning that if you plot level, this curve here, the slope or the rate of change of level will decrease, and that's really presented by this function here. Okay. Now if we look at this function in general, so this is the regular shape of a first order linear ODE model due to a change in the inlet in a step manner. Now what are the effect of this parameter? So if I take the base model to be this one, we'll compare with two models, model 1 okay. So here k1 greater than k and tau 1 equals tau. We'll take model 2, k2 tau 2s plus 1, here k2 equals k, but tau 2 greater than tau. Now how does this response look like? So we plot these three response here with time. Say for the same input change, if we take the same input magnitude for all these three cases, the base model would look like something like this one. For model 1, where k1 is greater than k, it will look like okay. And for model 2, where k2 is equals k, over tau 2 is greater than tau, it will look like this. So this is corresponding to model 2. This is corresponding to our model 1, and the other one is corresponding to this base model. Now what does it tell you? That if k is greater, the curve will go further up. Okay. However, if tau is greater, the curve will become flatter. What it simply means, this is k term that denotes how far the response will go, and the tau term will denote how fast will response move. And in fact, if you look at this response here, the final value is km, where m is the value of the input. Okay, so the output value is multiplied by this factor k. Okay, so that's why this k is called the gain. Okay, and this tau, which denotes the speed of the response, is called the time constant. Now let's look at the original equation we got for this model. So we had really this in this form, tau dh prime over dt h prime t. Here we had really the main function was so what we are calling tau is nothing but and what we are calling k is nothing but, now what it simply means that the A represents the area of the tank, cross-sectional area of the tank, H0 is the level at initial condition, C is some measure of this really resistance to flow, where we had C square root of H. Okay, so what it says that the tau depends on the area of the tank. Okay, so simply if the tau is area is higher, the tau is higher. So if you look at, if we have two tanks, suppose for this one, this is our base case, suppose this one we had this A2, where A2 is higher than A, that would result in the higher value of tau, meaning that the change in this tank will be slower. Okay, and that's understandable from the tank, right? If we have the same inlet coming in for a tank, smaller tank, or a big tank, the change in the level will be slower for the big tank and faster for the smaller one. On the other hand, we see that okay, there is no k term, there is no area term in k. What it simply means that if we make the same input change in tank 1 and tank 2, and if they are initially at the same level, the final level will also be the same. Meaning the gain of these two tanks remain the same. So the gain will not depend on the area. Meaning that it will initially go from same initial condition to same final condition. The second time it will go there. However, it will go much slower. But it will go to the same final condition if they start with the same initial condition.